Okay, so why it is not formed in 0 degree? Because the scanning vector, so how much that here when we change this what is a scanning strategy, the amount of time where your laser is interacting with the material will change. We call it as scanning vector. So this could be attributed to the higher niobium segregation as a result of varying cooling rate in the samples with infill rotation. So it is happening because your scanning vector changes, like vector length changes. Your vector length are very less for 45 and 67, but it is very big for 0 and 90. So 0 is very big compared with 90. So there is more heat is evolved. So your ray phases are not there. Okay, so it is type of research. If you have any doubt, you can ask me at the end. So this is the microstructure. We did EBST and we find out the size of the grain. So you can see it here clearly. This is the image of EBST. You can see bigger grains are formed in 0 degree because your melt pool is not braked. You are doing in the same direction. You can see at the next, you can see the gain gets refined because we are putting 0 and 90. You can see this is 45 and you can see lot of big, then this is 67. You can see here bigger grains and your grains get refined when we change the scanning strategy. So samples without infill rotation 0 degree shows an MDU of 11 point. It's very high. And if you see sample 67 and 45, it gives better, and you do the MDU value of 6.9. That's called weaker texture. Weaker texture is very, very important rather than strong texture, because strong texture, the problem is if you apply the load in that direction, you'll have a very good, what do you say, property. If you change the loading condition of the different direction, it will break immediately. Okay, so if you have a weak texture, any side 360 degree, if you load it, the life will be little more. So we need a weak texture of lesser MOU, that is 3.9 or 4, you can tell. And if you see the crystal orientation, it was greater, bigger for 0 degree, and next is 90 degree, and less than 45 degree, 67 degree. 67 degree is better with lesser MOU, we can see here. So from this, we can see 67 is better. Okay. So next we calculated the what hardness. So for 0 degree, hardness is very less, and 67 and 45 the hardness is better. For 90 degree, once again the hardness is dropped, because this is because of the grain structure. Because as I showed, as per Hall-Pike's effect, finer the grain, higher the mechanical property. So the grains are very fine with 45 and 65. That's why the hardness is done. So we did harness. Next, we did UTS and YS. So what is tensile strength and ductility we measure. Both things are very, very important. So if you see the tensile property of 67 and 45 is better when compared with 0 and 90. And you can see the ductility is very high for 0, and it is very high for 90, also very low for 45 and 67. Why the ductility is very high for 0 and 90 is the layers formation is very less in 0 and 90 because of the scanning vector. The layer formation with 45 and 65 is very high. That's why, because it's like a brittle material, it won't allow the material to extend. So that's why it was reducing the ductility. Okay, so these are the things we have found. So from this is a summary. We can outright reject 0 and 90 because 0 and 90 ductility is good, but other things are bad. Roughness is bad, hardness is bad, microstructure is not good. So we can right away reject 0 and 90. Now the trade-off will come between 45 and 65. You can see here 45 is the dark blue and 67 is the green. So now it's the trade-off will come between this dark blue and the green, because 0 and for 90 is completely moved. Now we have to make a trade-off. So if you see the texture, weak texture is also fine, but it has a 67 has a very weak texture, less than the 45. And if you see the ductility, I'll come to the ductility later. You see the hardness, 67 has more hardness, and 45 is also having hardness closest. And if you see the yield strength, green is having more yield strength, and if you see blue is having lesser. All three cases, texture, hardness, and yield strength, you have your 67 is acting as a superstar. It is giving higher value. But if you take ductility, you can see 0 and 90, I outrightly removed it. Only I have to check with 47, 45 and 90. You see 47, 45 and 67. You see 67 is giving very low ductility. Okay, ductility is very, very important for a component, because when you apply a load, your material should act as a ductile material, because it gives some time for your component to break. If you take a glass and throwing a stone, what will happen? Immediately the glass will be smashed into pieces. So ductility is less there. So if you take a metal, I'm throwing a stone, what will happen? It won't get, sometimes it will get bent and get the energy absorption. So I need my material which have some higher ductility. So what I'm doing, even though 67 is better, the ductility is poor for the 67. That's why I'm choosing 45 is my 45 is my optimum value, because I'm considering the trade-off of 45 will exhibit optimum yield strength, ductility as a result of refined grains exhibit a weaker crystal structure and produce isoprotic mechanical properties. Even though 67 is performing well with all the cases, ductility is very low. So I have to compromise ductility because that is the life of the component. So I'm taking 45. This is called trade-off. That's why I'm telling that in research we have to do lot of trade-offs. Okay, in life also we are doing trade-offs. So in research also we have to do lot of trade-offs. Okay, so this is how we can say I'm taking a very important parameters as scanning strategy. That is how it's affecting the component life, and we are completely, it's a research. We identify 45 will be the optimum scanning strategy for building this component. This is one of the, what do you say, one of the case study was did by my PhD scholar. Next, we will go to another capability. We are exploring another capability called FGM. What is called FGM? Functionally graded material. For giving that case study, I have to give some introduction about thermal barrier coating. So, what is thermal barrier coating? If you take all turbine blades, normally it's made of inconel. On the top of the inconel, what we will do, we will go for a bond coat. This the substrate backler is inconel. Over that we have a bond coat and we have a top coat. So what is the top coat? Top coat material will be mostly zirconia, vitrified zirconia, toughened zirconia, because it's a ceramic. And the ceramic directly cannot be coated on the top of the substrate, because the ceramic is a, what do you say, it's a top coat is a ceramic and the bottom is the metal, so it has some adhesive issue. So what we did, we will normally, what we will, they will do a bond coat. The bond coat will hold your top ceramics and lower metal. So normally we will do that. So we can see the SCM image. This is a stabilized zirconia on the top, inconel at the bottom, and we have n number of bond coats here. So we are using a bond coat to do. This is how the average or normal thermal barrier coatings will looks like. Okay, so this is done to protect your inconel from heat, because if it will be operated at 3000 degrees centigrade, if you put inconel will melt in that temperature. So what I want to protect my substrate. What I'm doing, I'm protecting the substrate with the top coat, that is ceramic. Ceramics has the property that won't, its melting point itself more than 5000 degrees centigrade, so it won't get melt, but it cannot be directly coated on the top of my substrate, so I'm using a bond coat. Okay, so this is the concept, what how it's manufactured in the thermal industry. By this is the example of TBC. Okay, so what are the challenges? This is the procedure. Okay, I'm in mechanical engineering or in any engineering, if there is an advantage, there is a disadvantage. What is the disadvantage of this is, like, after some time what will happen, the heat will flow through this ceramic and directly react with the bond coat and directly react with your substrate, and it form thermally grown oxides. So there is a chance of thermally grown oxides. Once this oxide layer grows, what will happen after some time, your bond coat and the top coat can be easily peeled off from your material. So this is the bond coat. On the top of this bond coat, you are seeing the orange line. Na? This orange line is nothing but TGO. What is called TGO? Thermally grown oxide. So the material from here substrate will move forward and they react with the temperature that is coming from that side, and it forms an oxide. Once again, oxide will act as a ceramic. So it's an oxide is like an oxide layer. So it try to peel off your top coat. Once that top coat is peeled, it will directly what is it? It will attack your substrate. So I want to protect that. Okay. So this thermally grown oxide is a challenge. This TGO. Okay. So the thermally grown oxide layer continuously grow at higher temperature, making the connection between the substrate and the top coat, which leads to failure. So this is about some introduction about thermal barrier coatings. Why I am giving this introduction? Because we try to make a turbine blade, or you can say we try to make a coating by using this LED technique, laser direct energy deposition method. Okay, so this is another research. This was done by one of my MTech student. What he did is he tried to. It's very difficult to make with additive manufacturing. We tried to do it. What we did, we plan to deposit, let's say that atria stabilized zirconia or some ceramic on the top of the inconel. Okay, so bond coats are used as a buffer layer to ceramic thermal barrier coating to the metal turbines. I told you in the previous slide. Due to oxygen diffusion, thermally grown oxides are there that will lead to coating. So now the problem is what's happening. Your oxygen is coming and it was your temperature is coming directly connecting with your what do you say, your bond code. From the bond code, you are getting what do you say, oxide layer coir, and it gets failed. So we sit and think whether we can print without a bond code. That is a challenge. So can we do it? We can do it, but the problem is how to make adhesive between a ceramic and a metal. So there comes a technique called FGM. So I will explain what is FGM. So this study attempts to fabricate novel TBC coating without bond coat material, because the TGO is formed because of the bond coat. Now we plan to remove the bond coat so that we can reduce the TGO by using a technique called functional gradient approach. So what we did, so we took this Etria stabilized zirconia, that is nothing but your what do you say, your top coat material, and we take the powder and we measure the powder size, and we try to measure everything and we print it. So we have a work plan. I shown in the work plan. We have printed 3 samples with different grading condition. I will tell what is grading condition in the next slide. And the machine is powdered to samples were cut across, and we are doing this. First, we'll see with the sample one. Sorry. So first we'll go with sample one. What is sample one? This is a substrate. You can see a substrate one. Over that I am directly printing 100% YSC without bond code directly. Please understand, I am not putting any bond code. Directly I am putting YSC. You can see the condition here. I did it. This is my first condition. There is no bond code and there is no FGM. Next, what I did, same substrate. What I did, I made YSC on the top. How I am making YSC, you can see 50% of YSC and 50% of Inconel. On that layer, 100% of YSC I am making. So this is called FGM. So I am not directly putting YSC on the top. What I am doing, I am taking the second layer I am making with 50-50. On the top of that, I am putting YSC. This is called FGM, functionally grading. Every layer, I am changing the percentage of your YSC and Inconel. This is the sample number 2. Next, we will see sample number 3. First substrate is there, 25 YSC and 75 Inconel, 50-50, 75-25 and 100% YSC. So if you do like that, you can completely remove the bond coat. If you remove the completely bond coat, there is a less formation of thermally grown oxides. So we did it, and you can see in the first case, after heat, what we will do, this is the case. This is the microstructure. You can see very few, one thin layer of Yttria stabilized zirconia is on the top, and you can see lot of cracks, as interpreter cracks are there, because the lower part is metal and the top part is YAC. So it is not at all working. It won't work. But we did for research whether it is working or not. If you see the second area, you can see this is the top coat, and you can see this is the bottom coat. You can see some of the layers get affected. You can, even though we see some layer, there are few cracks are there. So it shows this structure. So some of the interface of the top coat showing a good bonding compared with sample one. Cracks, even though cracks are seen in the top coat, and some unmelted particles also seen. Some of the Yttria stabilized is not at all what do you say, not get melted. You can see unmelted particles also can be observed. You can see. Then this is the final sample. See, you can see this sample plays a vital role, and it gives better results because you have 75% OAC, 25, 3 different layers are there in between. You can see the bond strength is good, and it is good when compared with sample 1 and 2. So bond seems to be good at the interface. The vertical cracks are evident. Is good. Change in the microstructure of the functionally graded has been observed. The microstructure of 75 OAC, if it shows a change in dendritic with no secondary arms, it gives better results when compared with 1 and 2. So there are some unmelt particles also there. I'll give reasons why that unmelt particles are not working, what is happening actually. Okay, so this is how we did. So we fought lot of challenges when we do this, because in industrial application, you can ask me a question, can we print this like this? Now it's very difficult, you can't print it because it has lot of issues. I will say what are the challenges in the issues. So this is the substrate Inconel. Over that we have a functionally graded layer, and over that we have, see, what is the biggest issue here is, see, your YSC particles are very less in density. So in the melt pool, when it goes, what will happen? Because of the Marangoni current or Marangoni convection, what will happen? Because of lesser density, what will happen? Your YSC particle will come on the top, and it won't avoid other particles to go down. I will show here. So this is called Marangoni current actually. Okay. So what we are doing, when the melt pool, the melt pool temperature at the core is very high, and the melt pool temperature at the end is very less. Because of that change in the temperature or change in the surface, what is the surface tension, your material tends to move like this. Okay, so what will happen? It will become it will make your particles inside the melt will rotate. As per what will happen, as per YSC has very less density, what will happen, all my yttrium sulfide signoria will be on the top, it will avoid other materials to go inside. That is the one of the problem. This is called Marangoni effect. What is Marangoni convection? The liquid moves from the region of lower surface tension to the higher surface tension. This movement create a current inside the melt pool. I am speaking about the individual melt pool. This is known as Marangoni current. So this is the technology. So what we did here is, the issue with this printing technology is, the your your YSC particle is on the top. That way, when you put automatically, because of less density, your particle is coming up and it was avoiding the next layer to come. So what we did here is, we reduce the size of your, what do you say, melt pool. How we reduce this? We reduce the spot size. When I reduce the spot size, what happened? When we go with normal spot size, what happen? All your OSC particles on the top. When you reduce the spot size from, suppose if you say 6 micrometers or 6.6 micrometer to, sorry, 6 or 6.5 micrometer, something to 12 micrometer to 6 micrometer, I have a very depth pool. When I get the depth pool, the current inside my Marangoni conversion inside my melt pool is very high because of the depth increase. Once the depth gets increased, what is happening? All my OSC particles are pulled in. So there is no very less particles on the top, so that I can directly put my other layer on the top. This is what we did, and it was very successful. This happened because we reduced the size of the spot. Okay, so OSC particles are homogeneously distributed within the matrix. The secretion of OSC particles in the top substrate were not observed like in this case. So this was a published paper. So we overcome this paper by changing the spot size. So homogeneous distribution of your OSC in the matrix due to the strong fluid Marangoni current. So how we increase the Marangoni convection? By reducing the spot size of the laser. The strong Marangoni result, the size of the laser is reduced. The spot size leads to melt pool, deeper melt pool, but it's not that much deep when compared with that. But even though we can do this technique, but it is commercially used or not, in future they will do it. Now it is one of the important study in the research community, where we proved that by using LDD process, by using FGM technology, along with reducing the spot size, we can print Etria Syncronia directly on the top of the encoder. That was the success story we did, and we applied for some patent also, still waiting for the result. Okay. So this is about the metal additive manufacturing process, where we used powder as a thing. Next, I am going to do one of my PhD students' work, that is on DED. Instead of powder, we use wire. That is, we call it as VAM, wire arc additive manufacturing technology. Okay, we'll see that. So the VAM is very, very famous in additive manufacturing because the deposition rate is very high. So I'll show a video. After that, I'll tell what is the advantage and disadvantage of the process. So this is a company called Relativity. That the company is inside NASA, and they are helping NASA people to build casing for their rockets and what is it, satellites and nozzles. So normally, if you want to make this casings, what will happen is, like, it will take more than 3 to 4 months to do it. By this additive manufacturing technique, within 15 to 20 days, this wire additive manufacturing techniques, they are doing it. That becomes, this company becomes very famous when they use this novel technology to build the casing. So this is called wire arc additive manufacturing. So we did some research in wire arc additive manufacturing also. I'll give some important advantage. Why this? What is wire arc additive manufacturing? It's a DED process only, direct energy deposition only. In that, what we are doing, we are removing powder and we are putting wire. That's it. So deposition rate, why it becomes very famous? Because the deposition rate is very high. I told you, can see directly melting the wire and depositing. If you want to make the casing in a conventional way, it will take more than 90 days or 120 days. But when we use VAM, we are making it within 30 days, 25 to 30 days. See how much time I am saving, how much money I am saving, how many people, because now it is everything get automized. There is no need of human intervention. So we can do it very fast. Okay. So that it makes this process very famous because the deposition rate is 10 kg. So it's an advantage is there will be challenges also, right? So advantages is less material wastage, low cost machine, low production cost, higher production rate, and higher percentage material utilization, superior layer fusion. Everything is advantage. What is the disadvantage? Is poor surface finish. Once again, it is very poor when compared with powder DED also. Tensile residual stress is very high because it's like welding process only. The deformation due to high input. See, if you know welding, you can understand spattering. Especially when we do with aluminium or when we work with magnesium rods, you will feel that spattering effect will be more. So the deformation will be more, less dimensional accuracy in staircase effects. So these are the disadvantages. So how we can overcome these disadvantages in VAM? What we did, these are n number of VAM setups available in the market. One is called GTAW, normally gas tungsten arc welding technique, plasma arc welding, gas metal arc welding. So these are the normal welding process that can be used for wire arc additive manufacturing. Because you can see here, this is called spattering. You are see this is somewhat good. You see this one, this is aluminium. If you go for hard materials like steel and other stuff, no problem. If you take material, soft material like aluminium metal, spattering will be more. So there come one of the there is a technique called CMT VAM. What is CMT VAM is called cold metal transfer VAM. So what is cold metal transfer is, you can see the video here. Here you can oscillate your what? Electrode. If you want to start oscillating your electrode, I can control my droplet. Okay. So if my droplet get break, and it can be controlled. Once it get control, what will happen? The spattering can be reduced. Because this oscillation, the amount of heat input in this area is very less. So this is called cold metal. Don't think cold metal means there won't be any temperature. Temperature will be there, but conventional heat source, when compared with conventional TIG or MIG, the temperature at the interface zone will be very less. So this is called cold metal transfer. If you use cold metal transfer, what is an advantage? What is a what is the advantage of cold metal transfer is 33 percentage lower heat than conventional VAM. Why I need this 33 percentage improvement? Because I can easily operate some easily thermally get damaged material like aluminium and magnesium can be easily manufactured by using this component. Because if we see most of the research in VAM, they only do it with inconel or steel, a very hard material. Aluminium and magnesium work is very less. That's why people researched and they did a machine called CMT VAM, where they reduce the heat input by 33 percentage. After they are reducing the heat input by 33 percentage, what is happening? We started using materials like aluminium and what do you say, magnesium. So this deposition is good. So this is buying technology. There we are oscillating our what do you say, electrode. Because of that, your droplet get break and it can be easily get deposited. This is called CMT lab. So what we did, the advantage of this is like one second. I'm audible, right? Am I audible?
Yes, sir, you are audible.
Oh, thank you, thank you.
Yes,
So
sir.
we have seen about what is wire harness additive manufacturing and its advantages, and we speak about CMT VAM. Now, what is the advantage of CMT VAM? We can play with material like highly heat sensitive material like aluminium and magnesium. But I started working with magnesium. Why? Because magnesium has lot of applications, starting from what do you say, aircraft cabin, fuel tank, petals. Because it's lightweight, especially in the field of biomedical. Drawbacks is also there, a lot of advantages is also there, disadvantages also. So nowadays magnesium plays a vital role, especially in the field of biomedical. Okay, so now people want to replace the titanium implant by magnesium implant, and now magnesium implant wants to be replaced by zinc also. People are doing a lot of work, and one of my other students also working on zinc. So why titanium we want to replace with magnesium? Because titanium, the problem is it is not that much biodegradable. If you want, see, normally most of the people who did some orthopedic surgery long back will face that issue. If you have a fracture, what they will do, they will put a titanium implant. After 1 or 2 years, they will say they will do one more surgery to remove the plate out after your bone get fixed. So people have to do two surgery and they have to bear the pain. It's very difficult. So they want to replace this titanium with a biodegradable material. Once I put the implant in my body, it has to dissolve immediately along with the brain without affecting our body. So magnesium is, our body need magnesium. So what they did, can we make an implant and we put it inside? Once your bone gets killed, the implant should be dissolved in your blood. That was the idea. But the disadvantage of magnesium is like, what will happen? It will fast, it will dissolve. The corrosion rate will be very fast. Before healing your bone itself, it get dissolved. That was the disadvantage. So people are doing lot of research. Was one of my research I did. What I did is I make an implant by using VAM technique, and I use surface modification technique to improve the corrosion resistance. Okay, that's what we are going to see in upcoming slides. Okay, so my third case study, VAM of magnesium, but I am not showing the surface modification. I will explain you how I manufacture the VAM. At start, there will be a what? A workflow. So this is the workflow. This is the machine what we used in Fornius Bangalore. This is the whole CMT setup, and we build the component. You can see the components doesn't look good because we did it in open atmosphere. So there you can see the oxides that looks as a black color. Okay, so this is continuous deposition with dwell time 10, dwell time 20, and dwell time 30. That is the dwell time is the time given between each layer. So seconds we will stop and we will do it. Okay. So first I have to do, this is the, what is it, single track. I said single track means the melt pool dimension. So I did some 9 single track experiment like this, and I did a cross section and I took the melt pool because this is a melt pool study. And I found that the H, what is it, the H, I have to rush up little fast because time is less. If you have any doubt, you can make a note, at the end you can ask. Okay. So this is the H, you can see. This is the melt pool, which has a proper, what do you say, deposition, and it has a very good melt pool shape and size. So we identified two, from this we identified two things, 6 and 7. After doing a trade off, okay, we got it with wire feed 8 and the travel speed 0.6, we are getting this melt pool. We found this is an optimum. With this optimum condition, we built the entire thin wall like this. Okay. So we built the entire thin wall. From taking this entire thin wall, what we did a cross section of the thin wall. Okay. So this is the thin wall I shown. Na? This is the thin wall. So now I am taking the cross section of the thin wall in the next slide. This is the cross section of the thin wall. You can see here. This is the cross section of the thin wall. How I built it? By optimizing my wire feed and travel distance. Now what I am doing, from this big thin wall, I am going to take the structures of the top, middle, bottom, and the substrate. Substrate is once again magnesium plate only. So now you can see the grain sizes are changing. So I want to find out what is a microstructure, everything. So what I did EBST. So EBST, after finding EBST, I can find the top size is my 58 micrometer, the middle is 63, and the bottom is 38, and the substrate is 12, because this is not VAMmed. It is like cast, not cast wrought. Okay, so this top bottom is 38, 63, and 58. So you can see there is a change of microstructure along the build direction. This is because of the heat transfer happening between your plates. So you can see here, this material is very close to your substrate, so the conducting mode of heat transfer is very high, so it refined the grain. And you can see on the top, the radiative mode of heat transfer is very high, because top area is 360-degree, it is exposed, so it also get a very fine grain. But if you see in the middle grain, only two sides radiation, the conduction is very less, so it has a bigger grain. So this is also identified. And what we did a porosity, that is called XCT analysis, and we took the complete thin wall and we did the analysis, and we found out porosity is also there. Then we found out that the UTS, yield strength, as well as the tensile strength, elongation, ductility, everything on two directions. What are the direction? Along the build and across the build we did. So these are the, to identify how is the strength of the material. And we did some texture analysis also. Texture is weak only, no problem, it's very good. So we identify the grain size, and we, by using the SEM and EBST, we found that all the grains are equast grains. You can see this is not bigger grain, fine, and equast grains. And the hardness is also good. It's like coming out like 58 to 63, and also tensile strength is also good. And now we got it good. So how we can say it's good? It should be compared with existing material, right? So what we did is we tried to compare VAM with cast and rod. Okay, this is this is rod microstructure, this is cast microstructure, and this is CMT VAM. So now I am going to compare it. So now you can see the tensile strength casting is very less because it has lot of casting defects. Now what I am doing is now I want to compare my data of VAM with rod. So now I can say it is little comparable. I can say the VAM is better than rod. Rod is always better because we are doing forging, something like that. So it's good. And compare with rod, it is slightly better, but it is better than cast. Okay, that's all. So you see the porosity level. Casting porosity is very high, VAM porosity is little lesser than that, and obviously rod porosity is very less. Grain size, if you see, casting grain size is very big, and VAM grain size is somewhat in between, and rod grain size is very less. Okay, so this is because best means, how will you compare? We have to compare best. VAM is best means how can I tell it's best? I should compare with the traditional processor. So when I compare with casting, VAM is better. With rod, it was slightly matching it. So we have a lot of research we can do to overcome, or it should become a better than rod. That's what researchers are doing. Okay, so this is one of the stuff. This is what we did in wire arc additive manufacturing. Now we'll see the future scope of AM. So another one case study also we did. So what will happen? That is called hybrid additive manufacturing. Why I want to do a hybrid additive manufacturing? See, this is DED, and this is called laser surface laser sinter. Okay, it's a SLM. We call it as surface laser melting. We call it as some structure. This is called laser melting. So we call it an LPBF. We call it the LPBF's other name is SLM. LPBF. There are two processes. That is called LPBF and laser LDD. The LDD we have seen, this LPBF. So what is the advantage here? LDD, the deposition rate is very fast. I can fill it. And my LPBF, I can make structures like this. You can see this is called lattice structure. It is not filled. You can see in between we have. So this complicated can be done. So when we combine this, we will get lot of information. So traditionally, I have a combination of 2 or 3 subtractive manufacturing processes, other processes to improve the productivity and mechanical properties. This is a hybrid. So I did one of my MTech student did a hybrid additive manufacturing. I'll show the image, then you'll understand. So we did two things. What we did is we took a substrate that is made of one material, and we made the overbuilt layer with other resource. So for first, what we did first layer we built. This is not VAM. Okay, this is VAM material. Instead of magnesium, we used aluminium. The first material is VAM. On top of the VAM, what we did, we printed LDED, the first case powder. This is wire and this is powder. Why? Because why I used, you can ask, why you build substrate by wire? Because deposition rate of substrate is very high. So I made the substrate by using wire. On that intricate features, if you want to add, I can add this powder. Now this is my VAM. On the top, what I have, DED. Now this is the structure I did, and we did the analysis on that. So we can see this is the first sample. We can see the VAM at the one end and inconel at the top, that is LDED, and wire arc additive manufacturing at the bottom. So this is a cross section. This is a coupon we made, and this is done by VAM. And this is on the top, that is LDD. That this is the machine formula in the machine we did it. So now we did hybrid additive manufacturing. So what is the challenge here? I want to find the interface bond strength. So we did scissors. So this is the microstructure. You can see this is top LDD layer, and bottom VAM layer is also here. Now I want to cross check how is my interface, whether my interface is good or bad. So we did some ABST analysis, and we did some shear model test, and we found out that interface strength is also very good. So you can see the microstructure change here. So LDD, bigger grains, because this is powder based. This is wire based. You can see finer wire, all equias structures here. So you can see the hardness of your VAM is less because this is steel. On the top, inconel hardness is higher, and you can see there is a change in the hardness from the hardness from the steel to the inconel. So you can see that. So the tensile strength is also good, stress is also good, and interface bond strength is also very good. We have seen that. Okay. So what are the key takeaways from this lecture is, we have seen three process important. So we have seen additive manufacturing. In additive before starting additive manufacturing, the important thing what you have to do is you have to do the melt pool optimization. Optimization of your melt pool and scanning strategy is very very important, because you have to make your unit cell better. Then only, because unit cell make the bigger component. So it is necessary to optimize your melt pool as well as scanning strategy. And there is a possibility we have seen by DED process, you can do FGM. That is an example, second example I'll show. Because without bond coat, we directly deposit a ceramic on the top of the metal by using a technique called FGM. That is also possible by additive manufacturing. Next is wire arc additive manufacturing. What is the advantage of wire arc additive manufacturing? Deposition rate is very fast, and very by using CMT VAM process. What we did, we use thermal sensitive material like aluminium or magnesium can be easily printed. So bigger large volume deposition of thermal sensitive metals can also be done. These are the two important takeaways. And the third important takeaway is that hybriding the process. So if I do hybriding the process, what I can improve the process. In this picture I'm showing laser as well as plasma. You can take two process, like any process you can take. You can take LPBF over VAM, or VAM over DED, or VAM over other process, other any metallic process also you can use. So this field is emerging as a focus in the research and development. It can be a transformation force in manufacturing. People like me and several people are working on it. And there is a growing interest in academia and industry. That's why we have this seminar, or this faculty improvement development program, where we need more people to involve in this research to get more advantages of this process. And there is an exploration to understand and leverage of hybrid AM techniques. So now future is hybrid additive manufacturing only. Okay. So before ending this lecture, I want to tell, most of us are researcher. I want to speak about Vishal Rao. That's a doctor. He's a Karnataka-based doctor. Now he's still practicing in Karnataka, in Bangalore. So he did one research. He's a doctor. Long back, I told a story. The first story is how doctors get the input from engineer, and they develop a product and they use the process. Here, what a doctor completely converted into an engineer. So what I have to tell, stop with another story. So this is a story of Vishal Rao. He is an oncology specialist, especially throat cancer patient. Okay, one day he was looking at the patients in the clinic, and one of the mango seller from Mangalore, he came and met him. So he has some issue with the throat. So once he diagnosed the throat, he found that he has an issue in the throat that is nothing but a throat cancer. And the mango seller told to the doctor, "Sir, I am day by day I am having get some money because of selling mangoes. If you sometime you are telling that my voice box, once you get cancer, your voice box should be removed." Okay. So he's telling, if my voice box is removed, how can I survive? Because with my mouth only I'm surviving. If you remove the voice from me, how can I survive? That was very pity. The doctor get confused what to do, and he told him, mango seller, so there is some devices that are available in the market. So we can put an artificial voice controller or voice modulator at your throat, so that you can speak. Then this mango seller asked, "Sir, how much is the money?" He told it comes around like 60,000 to 1.5 lakhs. And there is a mango seller told, "Sir, I am earning 500 rupees per day. So how can I offer or offered like 60,000 to 1.5? It's highly impossible." And that guy was literally crying and telling, "My voice is gone, my life is gone." He's went out. This created a big hurt inside the doctor's mind. So he did complete research how to create a small voice modeler, especially for this kind of people who can't afford this kind of high expensive what do you say, voice controller or modulator and the more. So he did lot of research and finally come up with a voice modulator. And you can't guess the price of this. Its cost of this is $1. Okay, $1 means somehow it's now 80 rupees. Now he's selling this voice model for 50 rupees. Okay, 50 rupees. Already existing one is like 60,000 to 1.5 lakhs. 6 months once you have to change it. This is same thing. It will give the same process, everything it will do, but the cost is only 40 rupees. Please understand. You even I'm why I'm telling this story is like a doctor he can do lot of research and he can directly impact the life of the people. Means why as an engineer why we are not doing it, why, whether you have taken any steps to do that? That is my question. I'm leaving the answer to you, what kind of research you are doing, whether so what he did is he developed this voice modeler and he put it in the patient. And what is the advantage of this thing is, the doctor don't need to put it in the operation theater to install this. He can directly take this op just like he had to put it in the throat. So he made it, and he made a beautiful thing. Normally what we do, if you find some invention or something, we'll make convert into a pattern and we want to sell by ourselves and we want to become a multi-millionaire, right? This doctor, what he did is, he don't want to make us a his property. He sells the patent. He make it as a proper property. Anyone in the world can download this design and they can make it by own. So this is the mindset of Indians. You can see this is the guy. This is the doctor named Vishal Rao. He didn't take the ownership of the patent. He give the patent for free across, not only to India, across the world. Okay, so this kind of people is also available in the what is available in our country. So this is the tradition what we are following. We whole India is here. We are working for other countries and other people. Normally we will do research in the benefit of others, not for earning money and all. Okay, so a country's to he is telling a country's to measure is not the success in GDP growth. What is the quality of life the citizens are leading? So long back, you cannot imagine a device for 50 rupees. Now he made it. Okay, so but we did and the power of people centric innovation is very, very important. So for if you are doing people centric innovation, additive manufacturing is a weapon for you, or it's a tool for you to come up with new invention. Don't think that mostly our researchers will think, sir, this machine what you are showing here is costing us 6 crores and 7 crores. In my college they won't give us what do you say, we didn't have the facility, and most of the college cannot afford 6 crores to have a machine in their college. It's very difficult, right? So how can we can do research? So the answer for this thing is like, you can develop a machine if you want, or else there are very low cost machines are available for 1.5 lakhs and 2 lakhs, 2.5 lakhs are available in the market. And you can ask me a question, sir, 2.5 lakhs, can we do metal manufacturing? Yes, we can do a metal manufacturing. There is a technique called FFF, filament fuse deposition. You can take a filament, bind it with metal, you can print by normal FDM, you do a what do you say, you do a thermal debinding and you can do a chemical debinding to get the material. That is one thing. You can make ceramics by ceramic printers. Ceramic printers cost is around like 3.5 to 4 lakhs. You can do research. If you have a will, you can do it. So a lot of applications and what do you say, processors are available in the market. Okay, so these are some of the facilities you are going to see tomorrow or day after tomorrow when we come to NITK. You can see the powder DED machines, and we have a very good facility for fatigue life measurement in CRF. And these are some of my current projects I'm working. Now I want to add graphene to the copper to enhance the, how do you say, some issues when we normally when we do additive manufacturing of copper, the laser reflective will be very high, so it affects the machine. So what we did, we add graphene to the copper and we are making nano composites. We can improve the deposition rate, as well as we can improve the mechanical property, like mechanical property strength, and also we can improve the conductivity of the material. So this is one of my student who is working on copper graphene nano composites we are working. Next we are doing another one work, like we are making nozzles. So how the nozzle will be like inconel. On the top of the inconel we have copper. Over copper chromium zirconia we have YSC, the TPC for a rocket nozzle. And we are using what I explained, right? We are using a what is it, FGM, a functionally graded material, to develop this. So first we have SS. Over SS we have copper chromium zirconia. Now this is an intermetallic. Over the intermetallic we will put nichrolene. This is another one material. This is a bond coat. On the top of the bond coat we can directly use ceramic material. Like that we are doing one research, especially for rocket nozzles, that we are currently doing. Okay. So with this I am closing today's lecture. I guess I have given some information about additive manufacturing and the areas related to that. Thank you for watching. And if you have any doubt, you can directly contact me through mail or my mobile phone. If you want to do some research here, you can directly contact me. I can show my lab to you when you visit here. You can do some few experiments here if possible. I can help you at my most. Okay. Thank you for listening. Thank you for giving me an opportunity to deliver this lecture. Thank you so much.
Thank you, sir. Dear participant, if you have any doubt, you can ask. Please unmute and please ask question. Is it audible?
Yes, sir. Audible, audible, audible.
Yes.
No doubts?
I think no doubts. Fine, sir. Uh, uh, it's my privilege to thank you.
Thank you so
On
much.
behalf of our organizing team, I extend a heartfelt gratitude for delivering an insight and engaging session on additive
Thank you.
manufacturing materials. Okay, during our faculty development program.
Thank
Thank
you.
you, sir. Thank you once again.
Thank you, sir. Thank you.
All these sessions is helpful
Okay, sir.
for teachers and faculty
Hello.
in
Okay,
their.
sir. Thank you so much.
Hello, sir.
Thank you, sir. Thank
Yeah.
you, sir.
Hello. Balan, sir.
Yeah. Yeah, please.
Yes.
Actually, we are planning to visit NITK on 30th.
Okay, sir. Okay.
In case if we get a chance to visit your lab
Yeah,
facilities.
please come, sir. I will show the small low-cost printers are there. That will be useful for your researchers to do research. Okay, I have
Okay.
developed a small lab where we have three low-cost printers. If possible, once you've seen the CRF, you come, and I will show my lab.
Thank you, sir. Thank you, sir. We will meet you on 30th.
So those who have doubt, you can come and personally meet and ask me the doubt. Okay.
Okay. Thank you, sir. Thank you so much.
Thank you, sir. Thank you.
Participants, please give feedback to Professor Balan sir. Feedback link is already shared in a group. Okay, please give feedback.
Okay, sir. Can I leave, sir? No. Fine, right?
Okay, sir. Thank you. Thank you so
Okay.
much.
Okay. Thank you, sir. Thank you.
Thank you, sir. Thank you.
Thank you, sir. Thank you.
Dear participant, our fourth session will start at 2 o'clock. Please come to online on time. Thank you.